Okay, so the next topic, okay, is about justifying the assumptions. So we have assumed the container containing the glass is a cube and the shape of the container is immaterial. For a vessel of any arbitrary shape, we can choose small, very small infant simul planar area, and can prove that above derivation. We can see A and delta are not there in the final result by Pascal's law. Pressure in one portion is an equilibrium in the pressure and it is same everywhere. All the collisions are neglected. The number of molecules hitting the wall in time del t was found to be 1 by 2 n into A into Vx into del t with random collisions and a steady state of gas. Thus, if the molecule with velocity Vx, Vy, Vz acquires a different velocity due to collision with some molecules, there will be always some other molecule with a different initial velocity which after a collision acquires a velocity Vx, Vy and Vz. Moreover, molecular collision, when they are not too frequent and the time spent in collision is very small compared to the time between collisions, will have effect in the above calculation. So when we consider the kinetic interpretation of the temperature, so the average what we call the average kinetic energy of the molecule is directly proportional to the absolute temperature of the gas, and it is independent of pressure, volume and nature of ideal gas. So we have to multiply V on both sides. So the equation will be after simplifying all the stuffs, so PV is equal to 2 by 3 n into 1 by 2 mv square. So the final equation will be like PV is equal to 2 by 3 kinetic energy, where E is kinetic energy, or E is equal to n into 1 by 2 mv square. So from ideal gas equations we know that PV is equal to mu RT. By simplifying all these stuffs, you'll be getting the answer as E is equal to 3 by 2 n kBT. So kB is nothing but Boltzmann constant, and kinetic energy is directly proportional to the absolute temperature. So we have to stick on to the kinetic theory a little more, consistent with ideal gas equation and gas laws. So you have to consider the ideal gas equation, that is for kinetic interpretation it is E by n is equal to 3 by 2 kBT, where E is equal to 3 by 2 n kBT. So here the internal energy of the ideal gas is directly proportional to temperature as well. So we can conclude that this energy is directly proportional onto the temperature, not only on the temperature but not on pressure or volume. So this internal energy is directly dependent on temperature, it is not depending on pressure or volume. And you have to consider the Dalton's law of partial pressure as well. So here from kinetic theory we have P is equal to 1 by 3 n mv square. So therefore if a vessel contains mixture of gases, we can take it as outside, that is 1 by 3. So n1 m1 v1 square plus n2 m2 v2 square up to m n m n n m m mn v2 n vn square. So this will be the equation, and if it is an equilibrium state, so average kinetic energy of molecules of different gases will also be equal. So it will be like half m1 v1 square is equal to half m2 v2 square is equal to 3 by 2 kBT is equal to 3 by 2 kBT. So the total pressure, we have to add it up and simplifying, we'll be getting an answer like P is equal to mu1 plus mu2 plus mu3 dot 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 close bracket of RT. So RT is a constant, so we will have like P is equal to P1 plus P2 plus P3 up to Pn, which is nothing but the Dalton's law of partial pressure. Okay, so in this video we discussed about the justification or the assumptions that we have considered in the previous topic, that was pressure of an ideal gas based on kinetic theory. We have considered few assumptions. So definitely in the cube the elastic collision of the gas molecules will happen in the with the wall of the container as well. So after that we discussed about the kinetic interpretation of temperature. We learned few formulas for it, and similarly the kinetic theory consistent with ideal gas and equations of gas laws. So thank you all.